One more example problem using conservation of energy. Here we have a block starting from rest at the top of an inclined plane. I'm envisioning it this way. So it says after sliding some distance, here's my block. After sliding some distance, it encounters a spring. So there's some distance here that it slides. I'm going to call this L. Hits the spring. But then, of course, because the mass has energy still, it compresses the spring, and it tells us the spring is compressed by 35 centimeters. Now, when the spring gets compressed, what was once the equilibrium position, meaning over here, I'm drawing that in because that's where we have to measure S from when we are accounting for the energy in the system because of the interaction with the spring. We have to measure S from equilibrium, meaning from here to here. So this S is the 35 centimeters. There is friction. They give us the coefficient of friction. They give us the mass, the angle of incline, so theta, the spring constant, and they're asking us, find the distance the block traveled before encountering the spring. So they're asking for this L. Now, if I were to represent where the mass was originally, the mass overall, this block, will travel both L plus S. The reason I'm mentioning that is because the force of friction acts the entire time the block is sliding. And so I'm going to call this whole distance our D. So when we say delta E thermal is the force of friction times D, I mean this entire distance. All right. Energy, there is a change in height in the problem, so we will need to consider gravitational potential energy. Kinetic energy, the block moves, so we need to consider that kinetic energy depending upon what we are defining as our initial and final moments. So when we write out conservation of energy, we have initial on the left, final on the right. So we're relating the energy in the system at some initial moment in time to some final moment in time. I'm going to choose my initial moment in time to be when the block is at the very top of the incline, and my final moment in time when my block has fully compressed the spring. You can split it into parts if you want. It's not necessary though. You could choose initial at the top and final at the moment it's going to run into the spring, but then you'd have to set up a problem again going from when it's hitting the spring to when it's fully compressed. It's one of the wonderful things about energy is we can just look at initial and final as long as we're accounting for any external work done during the process and any thermal energy generally or generated in the process. So no work external because we don't have any force outside of friction, gravity, spring that's responsible for changing the energy in the system. So let's talk about energy initially. We need to identify whether or not we have gravitational potential energy, spring potential energy, and kinetic energy at this initial moment in time. I hope it's obvious we don't have spring potential energy. The spring's not compressed yet. Nothing's stretching it out. It's not attached to the block. So there's no spring energy, or we call this elastic potential energy as well. There's not kinetic energy either, because the block, coming back to the problem, starts from rest. But the block does start at the top of the incline, so it is at an initial height. Now, just as a reminder, we can choose to define y equals 0. Oftentimes, we choose that to be at the lowest point the object will reach. So down on my second picture, if I draw a line right here where the block has fully compressed the spring, if I define that as y equals 0, then y initial is measured all the way up to where the block is. But, as in the previous examples, that height is directly related to that total distance d the block slides along the incline. We can say, as in the previous two examples, that y is equal to d sine theta. Oh, and that's initial, sorry, not final. All right, final moment in time. We are essentially defining no gravitational potential energy at this moment because we've chosen y to be 0 right here. There is spring energy. This block is compressing the spring, so we do need to account for that energy. Oops. Kinetic energy. Well, as soon as the block hits the spring starts slowing the block down. Eventually, or not very long per se, the mass will slow down, stop, and then the spring would push it back up the incline. So if I'm choosing my final moment in time to be this maximum compression, it's telling us it compresses the spring by 35 centimeters. That's assuming the most it compresses it. Then at this exact moment in time, there's no kinetic energy. That can be a little weird. We are choosing initial and final moments in time where there's no kinetic energy. And that's fine. It doesn't mean there's no kinetic energy at any point between initial and final. It totally does. If we were to watch this, we would see the mass slide down the incline and hit the spring. So keep in mind, with conservation of energy, we're just relating energy at 2 moments in time. Okay, so we're essentially saying that this system overall, the mass and the spring and the surface, all of that in this system is potential energy to begin with. And at this final moment in time, there's potential energy and some thermal energy that has been generated. So that's fundamentally what we're trying to write the equation to describe. So initially, it's all gravitational potential energy. Finally, it's potential energy because the spring is compressed, and thermal energy because the box, while sliding down the incline, friction was acting on it the whole time. And so those surfaces become a little bit warmer. Making some substitutions. For example, y initial being d sine theta, where theta is the angle incline, the 25 degrees. Friction force, coefficient of friction, mg cosine theta. But again, make sure we multiply by d, that total distance the box slides. to make it energy. So I should have chosen something different. We're finding D yet again, but this time it's on both sides of the equation, which is fine. There's nothing wrong with that. If I pull this thermal energy term over and factor out D, the negative sign ultimately means that friction is taking away from that original energy that the block had. All right, so D will equal K S initial squared over 2. I'm factoring out mg again just in terms of plugging it in my calculator. You don't have to do that. So K is 450. Decompression, I'm sorry, this isn't S final. I'm not sure why I'm trying to make that S initial, because I wrote S initial over here too. The spring's not compressed till finally. I apologize, I put an initial subscript on that. So 450 is the spring constant. The spring ends up being compressed by 35 centimeters, which we need to be in meters. We square that. The mass is 6.4 kilograms. G is 9.8. Sine, our angle is 25 degrees. Coefficient is 0.16. So I'm going to plug this into my calculator. I'm getting 1.583, which we have, what, 2 sig figs because of mu. This represents the total distance, again, we wrote it D, the total distance the block slides down the incline. So from rest until it's at rest again, from compressing the spring. This problem is asking us to find the distance the block traveled before encountering the spring. So if you noticed before, I was drawing L and S in my picture. So L representing the distance the block slides until it hits the spring, and then S is how far it compresses the spring. The problem wants L. So L, we just need to take what we just found, this total distance, and subtract off the distance the spring was compressed. So 1.23, and again we had the 2 sig figs, so 1.2 meters is the distance the block slid prior to hitting the spring.